All right, everybody, welcome back to your one-stop shop for the proof of Fermat's last theorem. Just a heads up, I am going to be on vacation this coming week. I'm still going to try to put up videos 5 to 6 days a week, but it's all dependent on internet connection, so we'll see what happens. Today, we're going to briefly talk about the curves field correspondence, which is a result we'll need a couple of times in this chapter, chapter 3 in my notes. So first of all, let's start out. What is a function field? Some context, an important theorem of basic algebraic geometry that relates curves and their function fields is going to be used more than once in this chapter. So I'll list a basic version of it here just for reference. I'll even list a less basic version of it here. I won't list the most rigorous version of it though. So let's let K be a field. A function field over K is another field called K prime, such that when you take K prime and you intersect it with K bar, the algebraic closure of K, you just get K. And I also want to require that the extension K prime over K adjoin T is finite, where T is some transcendental element over K. Okay, and then I'll also say that two function fields K1 and K2 over K are conjugate over K or K isomorphic if there's a K isomorphism from K1 to K2. What's a K isomorphism? It's an isomorphism between the two fields that fixes K pointwise. So it fixes the base field K pointwise. All right, so what's the field of rational functions on a curve? Let's let C be a non-singular projective algebraic K curve. Okay, so you can think of a curve as a complete one-dimensional variety, if you like. Okay, and so projective, I want it to sit in projective space. Algebraic, I want it to be cut out by polynomials. K curve, I want those polynomials to be defined over K. Okay, so let's define K of C to be the set of rational functions in K bar of C, where K bar of C is the set of all rational functions on C, to be the subset of K bar of C of functions defined over K, of course. So more precisely, I want K of C to be the set of all rational functions, big F equals little f over G on C. So rational functions on C, such that F and G are in the coordinate ring of C over K. So they're in K bracket C. What's that? Well, you can think of C as being cut out by an ideal of functions in K adjoin, or in K bar adjoin x1 through xn, let's say, where x1 through xn are just variables. So what I want to do is I want to look at the coordinate ring just defined over K though. So I'll take K adjoin x1 through xn, and I will mod out by ik, where ik is I intersect the polynomial ring in n variables over K. And what is I here? I is the ideal that's in K bar x1 through xn cutting out C. Okay, so let's backtrack. So you've got some curve C. Initially, it's cut out by some ideal I in K bar adjoin n variables, let's say. Okay, but I want to look at the set of functions defined over K on C, not the set of functions defined over all of K bar on C. So what I'll do is I'll take the coordinate ring of C defined over K. So I'll take this ideal that cuts out my curve C. I'll intersect it with the polynomial ring in n variables over K, because I is presumably just defined over K bar. That'll give me some ideal. It's sort of like the ideal cutting out C, but defined over K instead of K bar, and I'll call that ideal IK. And then I'll take the polynomial ring in n variables defined over K, and I'll mod out by that ik. And that gives me the coordinate ring of regular functions on C. And then quotients of those will be the set of rational functions on C defined over K. Okay, so if you haven't seen any of this before, I would say like Hartshorne chapter 1 is a good reference, the Shafarevich books, any of the references on algebraic geometry I gave in my first few videos, giving references for the proof of Fermat's last theorem, those would all be good references. Okay, so just think of it as rational functions on your curve C that have coefficients in K if you want something really easy to latch onto. Okay, so that's what K of C is, where C is a non-singular projective algebraic K curve. Let's talk about pullback briefly. If C and C prime are non-singular projective algebraic K curves, and H from C to C prime is a non-constant morphism of curves defined over K, then, as mentioned several times in my videos, H must be surjective. Okay, we've got this pullback map, H upper star. It's a map of function fields, H star. It goes from K of C prime to K of C. And what it is it takes in a function F here in KC prime, and it just composes with H. In other words, it pulls the function big F back through the map H. So you start out with a function F on C prime, you compose with this H here. Lo and behold, now you've got a function on C, right? Okay, so it's a map from KC prime to KC. We call this the pullback map. Okay, so here's the correspondence. I'll call this the curves field correspondence, or the curves fields correspondence if you like. What it says is the map that sends C to its function field defined over K is a bijection, or induces a bijection, from the set of K isomorphism classes of non-singular projective algebraic K curves to the set of conjugacy classes over K, or the set of K isomorphism classes of function fields over K. Okay, so this is something that's kind of unique to dimension one, right? K isomorphism classes of K curves are the same as K isomorphism classes of function fields over K. So you can think of curves like as their function fields in a sense, right? Moreover, if C and C prime are non-singular projective algebraic K curves, the map that sends H to H upper star is a bijection from the set of non-constant K morphisms from C to C prime to the set of K injections of the function field of C prime defined over K to the function field of C defined over K. Okay, so there's this correspondence between morphisms of K curves and injections of their function fields going the other way. That's what's happening here. You see the directional switch of the arrow. Proof, this version of things is discussed in Hartshorne Algebraic Geometry 1.6. In fact, I can give you a more precise statement that's more powerful and also discussed in Hartshorne 1.6. I'll give you the categorical curves fields correspondence. It says the following three categories are equivalent. Okay. Category of non-singular projective K curves with the maps being dominant K morphisms. A dominant map is a map with dense image. Okay. Quasi-projective K curves, dominant rational K maps. Quasi-projective varieties, just like an open subset of a projective variety. And a rational map is a map that's maybe not necessarily defined on the entire domain, but it's defined on an open subset of that domain. Okay. And then the third category is function fields of transcendence degree 1 over K, which I won't describe here. And the maps there are K homomorphisms, those injections of function fields we talked about earlier. Okay, and you can do even a little bit better than this once you know scheme theory. I would see Vakil's notes for that. Okay, and so tomorrow we'll start pressing towards talking about modular curves defined as complex curves. So we'll have to set that theory up first before we talk about them as algebraic curves over Q. So thanks for watching, and I'll see you then.